Okay, so all right, if you will request it to be recorded, go ahead and start it. I will give you guys the permissions. All right. Yeah, Matthew, if you want out the class, you can stay back and I can show you the previous lecture now, and you can take a snapshot of that on your phone. You can take a look at that. Yeah, sounds good.
Yeah, that sounds great.
All right, so 11.3, okay. So in 11.2, we're looking at hypothesis testing for the difference of two means where they are depend on each other, right? So the way to do it is you have to find the differences and then use that differences to do the hypothesis testing, right? 11.3, we also focus on inference about the two means, but in this situation, we have an independent sample, meaning that event A doesn't have effect on the event B. And this one here, it doesn't have to be that they have to have the same sample size, right? I could have 20 sample for the first event, and you could have 30 sample for your own event, and then we can do a comparison between those. All right. In 11.2, they must have the same n. In this section, that is not a required. So this is one of the hints that you might tell the difference between 11.3 and 11.2. Okay, just in case you saw that on the exams. All right. Because they doesn't require the two sample to be have the same size. Therefore, we can really take the differences like we did in section 10, 11.2. Therefore, we just have to find each individual means, and then we take its differences. Okay. So the requirements also very familiar with chapter 10, right? Either they are normally distributed or the sample size is large enough, right? For something to be sufficient large, we're looking at n is bigger than or equal to 30. So one of those conditions satisfied, then we should be good to go. Right? So for the confidence interval, what we need to do, we need to have is x1 bar minus x2 bar, and then plus or minus e. All right, and then the margin of error will be a t alpha over 2, right? So regardless of 11.2 or 11.3, we're still using t alpha over 2 because that anytime we talk about the mean, we're going to use the t distribution, not the z distributions, okay? And inside here, we have s1 squared divided by n1 plus s2 squared divided by n2, right? And since they don't require the two samples to have the same size, therefore, when we are choosing the degree of freedom, we might stuck in considering like which one should we choose? Well, for this situation, T alpha is computed based on the degree of freedom of the smaller sample size, meaning that we don't need the large sample size to do to find T alpha over 2. We only need to use the event that have smaller size. Okay, so that's how you want to choose which degree of freedom are we look into. All right. Okay, so keep that in mind. Make that note for yourself on the exam. Okay, so that you say, okay, now I have two sample. Which one do I go for? Always go for the smaller size. All right. And so after we find the margin of error, then we can find the lower bound, which is x1 bar minus x2 bar minus e, and then upper bound will be x1 bar minus x2 bar plus e. All right. So that's what makes it different between 11.2 and 11.3, right? Even though they both talk about the mean, but 11.3, they are independent from each other. Okay. And here is one example. All right, do men talk less than women? All right, The accompanying table gives the result from a study of the words spoken in a day by men and women, right? Um, let's construct a 95% confidence interval for the difference between two population means. And you can see here the keyword is, population mean. We know right away it's have to be, chapter 11. All right. So on the left-hand side, we have a sample size for the man will be 186, and then the sample size for women will be 210. So you can see here, the number of words the men are talk a day does not affect the number of words the women talk a day. So obviously they are independent from each other. And you can see that N1 is 186, N2 is 210. Therefore, it's no way they are dependent on each other, right? So like what we saw in 11.2, that they have to be the same size no matter what, right? So look out for those information on the final if you can, right? So that you get yourself the right formula to plug in. Okay. Okay. So x1 bar is given, right? And then x2 bar is given, and s1 is given, s2 also given. The only thing we need to figure out right now is how do I find the margin of error, right? Since N1 equal 186 is smaller than N2 equal 210. So degree of freedom will be 186 minus 1, which is 185. Okay, and that's very important. Okay, and now we can start finding the degree of the margin of error, and also T alpha over 2. Okay. So we have 95% confidence. Therefore, alpha will be 5%. In other words, alpha over 2 will be 2.5% or 0.025. So T alpha over 2 equivalent to T of 0.025. And this pretty much gives us inverse T. 1 minus 0.025, comma 185. Right? So it depends on the degree of freedom of the smaller size. All right, so I'm getting 1.973, right? All right, so that's T alpha over 2, which means that margin of error will be 1.9729 times square root of A632.5 square divided by 186, and plus with 7301.2 square divided by 210. Okay, so that's the margin of error that we're gonna have. All right, so we have 654,490.8039. Okay, and then square root of that, and then times T alpha over 2. We get 1596.088. All right, so after we find the margin of error for the means, then we can go ahead and find the lower bound for their differences. Okay, so I have here my lower bound. All right, so we take in x1 minus x2 minus e, so we get 15,668.5 minus 16,215, and then minus with 1596.088. So we have negative 2142.588. Then my upper bound will be 15668.5 minus 16215, and then plus with 1596.088. So I'm getting 1049.588. Okay, does that make sense? Mm-hmm. Yes, Matthew.
For the inverse t,
Yes.
is that 1 minus 0.025?
Yes.
So you put in whatever that equals into the area for the inverse t, right? So you
That's
put in
right.
like 0.9175 or whatever it is.
Yeah, so you second verse, and then when you do inverse t, all right, and then for the area, you just put 1 minus 0.025. Then degree of freedom, just put 185. Yeah, just put exactly how you saw it on the notation on the formula itself, and then just do like that. The calculator understood it. Okay, you don't have to do that subtraction first. You can just put in there in one strike.
Okay.
Mm-hmm.
So could you interpret the results of these bounds? Because I'm not too sure if I understand what negative 2,140.
Yeah, so for example, we are assuming that okay, the man should talk the same amount of the woman per day, right? Meaning that the center will be 0, right? But now with the margin of error, you can go, because we are look at their differences. So it could be that they could go less on here or more, right? So they can go on negative 2142 all the way to 1049, meaning that the man can talk less than woman all the way down to 2100 words, or they can talk more than a woman all the way to 1049 words.
So basically, it's saying that the mean words for men can be 2,000 words less than women or 1,000 words more than
They're different. That's
Got
right.
it. Got
So technically we assume that they are talking the same. So if they talk the same, then the difference would be 0. But that's just the point of estimating, right? So we assume that 0, but then what's the worst case scenario is men talk less than women around 2100 words, or they could talk more than women about 1049 words. Yes, Matthew.
So the answer to the question, do men talk less than women, is that a no or unknown?
For now, we just calculate the confidence interval, and in order to decide, we have to look at the hypothesis testing. because
Oh.
you can see here, well, they only survey 186 men, but they survey 210 women. So if we look at the amount of word they talk here, you can see clearly women talk more than men. But it's not going to be a fair comparison because one is have a smaller size than the other, so we cannot base on that. Yeah.
Yep.
We have to do a hypothesis testing to see which one whether it's passed the test or not.
Okay.
All right.
And are these actual numbers from an actual study or?
Yes.
Cool.
That's one thing about stat is we cannot make up stuff.
Okay.
Yeah. So that's why in every example I have to kind of tell exactly where it came from, right? So that's the resource that we're going to have. Yeah. Yeah. I won't be able to make up those numbers because what happened if I mess up the calculation and stuff, right? Yeah. So no. Okay. Sounds good. All right, so now to answer Matthew's question, we're going to jump into the hypothesis testings. So as you can see, very different from what we saw in chapter 10, right? We do have a number to compare with. Here we don't have a number. We just put it down mu1 equal to mu2 because that is the assumption. We try to assume that they both talk the same or everything will be equal to each other at the beginning, right? So mu1 equal to mu2. And then when you look at the alternate hypothesis, then you have three scenarios again. Mu1 doesn't equal to mu2, mu1 less than mu2, mu1 is more than mu2, depend on left tail, or right tail, okay? And you can see here, it's very similar to section 10.2 where we talk about the mean, right? As long as the two sample size is more than 30 or the population are normally distributed, then we should be good to go, all right? So that's the condition for us to check. And then as user business, you have to circle two tail, left tail or right tail, and then you write out the null hypothesis and the alternate hypothesis that we're gonna have. And then the only thing different will be step number 4, where we calculate T naught, right? So T naught we have to do is x1 bar minus x2 bar and divide by the square root of s1 square over n1 plus with s2 square over n2. So that's the only thing that's different from what we saw in chapter 10 when we focus on the hypothesis testing for the mean. Okay, so that's what happens with that. Okay. All right. So if I can bring back chapter 10 for you guys. Let's see, it's loading. Okay, so for the chapter 10, right, the T naught is x bar minus mu because we do have a fixed number to compare with, but here we don't. So therefore we have to take the difference between the first mean and the second mean and then divide by radical of s1 square over n plus s2 square over n. And number 5 is as usual business. Find the p-value, so it doesn't change much from what we saw in chapter 10. Right, so we still have two tail where we have to find the absolute value of T naught, and then you times it by 2 for the right tail. And the left tail, same thing, negative 10 to the 99 T naught and the degree of freedom. And then the right tail, TCDF, T naught 10 to 99 and degree of freedom. And remember, right, the degree of freedom is based on the smaller sample size. Okay, so that's something that we need to look out for. And step number 6, usual business again, we always compare p-value to alpha. If p-value is less than alpha, then we reject the null hypothesis. And conclusion, based on step number 6, we can state the conclusion whether we have sufficient evidence to support the data, the claim, or we have insufficient evidence to support the claim that we start at the beginning, right? That's very important, okay? Yeah, so if you feeling okay with chapter 10, then chapter 11 is just another, you know, smooth roller coaster ride, pretty much. Okay. Any question before we take a look at the next example where we do the hypothesis testings?
What are these formulas for?
Which one, Grayson?
The 2 TCDF T naught 10 to the 99
That's how you find the p-values.
p-values for testing what?
Because you have to compare p-value to alpha, just like similar to chapter 10, Grayson.
Yes,
Yeah.
I get that, but for example, when we test p-values, we could be testing the standard deviations, we could be testing the mean.
We're testing the differences.
Differences of
The
means?
probability of the differences between the two means.
Got it.
All right. That's the assumption, Adam. Yes. Always. All right. So using the given information from example 1, test the claim that the mean number of words spoken in a day by men is less than for women. All right. So that's the claim, right? The claim is the word spoken in a day by man is less than a woman, right? For woman, okay? Okay, so check conditions. We know N1 is 186, so bigger than 30, all right? N2 equal to 210, also bigger than 30, all right? So we're good to go, all right? All right, so very clear that it is left tail because that the man is talk less than a woman, so that would be left tail, right? All right, so the mean word for the man is equal to the mean word for the woman. That's the assumption. And then the mean word spoken by the man will be less than the mean word spoken by the woman. So that's the alternate hypothesis. Okay, it's left tail. That's what it is. Yeah. And then we calculate the test statistics. So we have T naught equal to x1 bar minus x2 bar, and then divided by the square root of s1 square over n1 plus with s2 square over n2. And if we take a look at the data that we saw in example 1, that's what we're going to use to do for this exercise. All right, you can see here x bar for the man would be 15,668, right? So that's what it is. And then for the woman will be 16,215, and then A632.5, and then 7301.2. So those are the information that we will use to do the hypothesis testing, right? All right, so X bar, I have 15,668.5 minus 16,215 and divided by the square root of A632.5 square divided by 186 plus with 7301.2 square divided by 210. Just use the calculators and see what do we have. So we get negative 546.5 right on the bottom. So let's see what we have here. So we have A09.006. Right? All right, so we get negative 0.6755. Okay, so step 4 is done, right? So we got those numbers taken care. And step 5 is just, draw a diagram and see what we can do for the p-values. All right, so this is left tail. We get negative 0.6755. So we want the area to the left. So my p-values equal to t probability of t naught less than negative 0.6755. And that's equivalent to TCDF negative 10 to the 99, comma, negative 0.6755, comma, 185. And you know why I use 185, correct?
Yeah, because that's the degree of freedom based off the sample size of men, which is smaller.
That's right. So that's the deal, right? So since N1 is smaller than N2, so we're going to use degree of freedom of N1, right? So that's how we got 185, okay? Then, put in to the calculator and then see what we get. All right, so now the p-value is 0.2501, okay? Now, okay, and then comparisons, as usual, right? We always use the statement. If p-values is less than alpha, then we reject the null hypothesis. My p-value is 0.2501. Alpha is what the alpha over here, right? All right, so what is alpha for this case? Well, remember they're all connected. So over here, we have 95%, therefore alpha will be 5%, right? And we can use that to use alpha as significant level, okay? All right, so from example 1, we have 95% confidence. Therefore, alpha will be 5%, which is 0.05. And that's what we're going to use because they're all going to be connected with each other, right? So alpha will be 0.05. And you can see here that, 0.2501 is not less than 0.05. So do not reject the null hypothesis. Conclusion is where we state the claim, right? What's the claim? The claim is the mean number of words spoken in a day by men is less than that for women. So we don't have enough information to support that claim, right? So since we do not reject the null hypothesis, there is insufficient evidence to show that the mean word spoken by men in a day is less than that for women. That's right, Adam. Sorry. So if you want to prove it, we would have to collect more data and see what can we do better, right? For example, you want to improve the result, right? We are collecting 210 women, but we only collect 185 men. So we might, collect more sample size for the men, right? To the point that they close to the woman, so we can go back and support the data. Yes, Matthew.
What did calculating the lower and upper bound actually do for this equation?
Yeah, so first, when you calculate the upper bound and lower bound, we just try to see, okay, if we want to publish this result, how confident we are. If we are 95% confident, that's, the different words spoken by men and women by how many, and when we publish that, what is the margin of error that we might make a mistake on, right? So this is based on a study, but in reality, we have to involve the margin of error, and that is the margin of error within acceptable range of 95%, Matthew.
Okay, so it's just kind of proving the data doesn't really relate to the next part of the question.
Yeah. Mm-hmm.
Okay.
Yeah, as I mentioned before, right? When we drive on the freeway, the speed limit is 65, but if you do a 70, the police doesn't stop you because that's the margin of error of 5 miles per hour. Yeah.
Got it. So that's that part of it. Okay.
There you go, Adam. You can collect more that. But no, but that might happen to the convenient sampling, Adam. Yeah, it's. Remember, we have to randomly select people, not like, oh, I'm gonna ask people in my family, right? Otherwise, yeah, it's biased. Yeah. You know, I don't know, but if I can talk to somebody about like soccer or car, I can talk all days. Yeah, so that's my chance to result, Adam. So men talk less than women based on this study is not really really true, right? Well, we did not disprove that, but it's not really true. Okay. Who agree men talk more than women? Can you raise your hand up? Thumbs up if you agree men talk more than women. No, Matthew say no, other way around. Hey, but the study show show something else. Okay, so how's the material for chapter 11 so far? 1, 2, 3, not too bad. Yes, very very clear distinction, right? In 11.1, it all focus about is proportion. That's all it does. And we have you two population. 11.2, the mean, but one thing that you can check that they needs to be the same data, and they have to relate with each other, right? That's how it is. 11.3, it doesn't have to be related to one another. Okay. and 11.4. All right, so we focus on inference about two population standard deviations. Okay. Okay, so for this, we going to use what is called is um, the F distribution table, right? We call this Fisher table, right? Because that's when statistician Fisher, inventing this one here and study a lot on this. So therefore, that we just call them after him, right? All right. So when we have one population, we use chi-square table. But now, when we have two population, we're gonna use the F table. So this is how we using the F table. F will equal to S1 square divided by S2 square. And this one here, you don't need to decide which one has to be the degree of freedom because we're gonna use both. We're gonna use degree of freedom of the numerator and degree of freedom of the denominator. And of course, we know right away, degree of freedom of numerator depend on S1, so that will be the first sample. And then degree freedom of denominator will be related to S2, will be the second sample that we have. And very important that we don't go from negative infinities, but we start from 0 to positive infinity, because similar to the chi-square, it's only take positive answer. So we're gonna go from 0 to positive infinity, and it is skewed to the right. It's not symmetric like the T table or the Z table. So anything dealing with standard deviation is not symmetrical. Therefore, the one on the left and the one on the right will give us two different numbers. But what we focus on here is how do we do the hypothesis testing for that, right? So we still be able to use a calculator, right? So don't stress out about that. Oh, do I need to know another table? The answer is no, you don't have to, right? So we focus on that. All right, so the setup for hypothesis testing will be, sigma 1 equal to sigma 2. That's always the initial claim, right? So you have two population, but they should be equal to each other, right? So that's the way to go. And then the alternate hypothesis, sigma 1 equal to sigma 2, sigma 1 less than sigma 2, and then sigma 1 is bigger than 2 sigma 2, right? So those are the three scenarios we always face with throughout the past week, okay? And the only condition is, the population are normally distributed, and that's the only one to check for. And circle the claim, right? Two tail, right tail, left tail, and write out the null hypothesis and the alternate hypothesis. And then if you look at step number 4, when you calculate F naught, it will be S1 squared divided by S2 squared. Very simple and straightforward. And step number 5, draw a diagram and find the p-values. So remember, anytime that you involve, chi-square or f, we have to do a comparison between the two populations to see which one have a bigger standard deviation, right? So remember in chapter 10, all right, we have for two-tail especially, we have to see whether S is bigger than alpha and then sigma, or S is smaller than sigma. Then we choose a formula accordingly. So chapter 11 is no different. So now you have to decide, right? And then this is only applied to two-tail, left tail and right tail. You don't care, okay? So for two-tail only, if S1 is smaller than S2, then we have to use the first formula. So the first formula will be 2 times the probability on the left-hand side, right? If S1 is smaller than S2, then we look at the left-hand side area. If S1 is bigger than S2, then we look at the right-hand side formula and double it up, right? So that we don't have to calculate the left and calculate the right, right? So we just based on that comparisons, okay? So the command will be 2 times F CDF 0 F naught, degree of freedom of the numerator, and then degree of freedom of the denominator. So that's the first scenario. For the second scenario, it will be 2 times FCDF, and then you have F naught, and then 10 to the 99, and then degree freedom of the numerator and degree freedom of the denominator. And that's how you put in that command, right? So there's no hesitation that, okay, which one do I have to use because I have two samples here. It doesn't require that, right? So standard deviation, they require us to do both of the degree of freedom. And for the left tail, you go from 0 to F naught. For the right tail, you go F naught to 10 to the 99. And you still need degree of freedom for the numerator and degree of freedom for the denominator. And here is the calculator instruction. You want to get the FCDF, you're gonna press second bars, and then you select FCDF. Then you're gonna ask you for the lower bound, the upper, and then degree freedom of numerator and degree freedom of the denominator. Okay. So I just want to show you where you would get that concept, right? Press second and star and bars. Then you can see here all the lists that we already become familiar with it. And then you go down one more, right? 0, you will see FCDF, and that's what we need, right, for the standard deviation of the two populations. Okay. And then number 6 and number 7 will be the same throughout any section from chapter 10 all the way to chapter 11. Okay. If p-value is less than alpha, then we will reject the null hypothesis. That's all we go for, right? All right, any questions, comments on this table before we, on this page before we take a look at a couple of examples?
Can you scroll up to the page prior?
Mm-hmm.
Okay, I just didn't know if you put in any notes. I thought I might have missed some, but no.
All right, so when you write your notes, please go in that orders, okay? So make sure you write those commands, right? If I ask you this kind of question, the layout will be exactly the same how on your second exam work, right? I'm gonna give you step 1 to 7, but then you have to write out, how do I find the area or the p-value for two tail, left tail and right tail, right? So make sure you write that. Just in case you guys missed this yesterday, right? I mentioned before, now you can have a double-sided note on the exams, on the final, okay? Okay, in Space Lab Life Science 2 payload, 14 male rats were sent to space. Upon their return, the red blood cell mass of the rat were determined. A control group of 14 male rats was held under the same condition except for the space flight as the space rats. Their red blood cell was likewise determined when the space rat returned. So the sample standard deviation of the red blood cell mass for the experimental group is 1.017 and the control group is 1.005. Is the standard deviation of the red blood cell mass in the fly animal different from the control animal at alpha equal to 0.05 level of significance? Okay, which one? Two tail, right tail, or left tail?
Two tail.
Two tail, right? Very clear, right? Very clear message right there. It's two tail. Thank you. All right, so we know it have to be two tail. So the the null hypothesis, sigma 1 equal to sigma 2, and then alternate hypothesis, sigma 1 does not equal to sigma 2, right? There's no need to show any number, right? We just have that claim between the two populations. Okay, and the claim is the standard deviation, that's the claim, right? The standard deviation in the fly animal is different from the control animal, right? So that's the claim. And let's see if we can agree with that alternate hypothesis or we cannot agree with that. F naught equal to S1 square divided by S2 square. So we have 1.017 divided by 1.005 square both, right? Let's see what we get. So we have 1.024. Okay. Okay, so N1 is 14, so their degree of freedom will be 13. N2 also 14, therefore degree of freedom also 13. Right? And then draw a diagram and find the p-values for this. So this is two-tail, okay? So when you have two-tail, you're gonna look at this one here, right? It have to be one of these two cases. Now S1 is smaller than S2, or S1 is bigger than S2. So S1 is 1.017, S2 is 1.005. So which one are we following? Smaller than or bigger than?
Bigger.
Bigger, all right? So S1 is bigger than S2, so we have to go with this formula, right? So
how do we determine which one is S1 and which one is S2?
yeah, it's always gonna go in that order of the claim.
As in, like, why isn't the control group S1?
No, control group is 0.05.
Yeah.
So they always go in the order of the claim. They said the red blood cell of the fly is different from the control one. So the one in the space will always be the first sample side in that orders.
Okay.
Makes sense?
Sorry, can you repeat that one more time?
Yeah, because if you notice any stat problem, right? The first thing they mention always the first sample, right? So this case here, N1 is 14, yes? And then you go on the next one, right? A control group, so that will be N2. They always go in that orders for the stats. Yes, Jackson.
For these type of questions with the two population standard deviations, would N1 ever be bigger than N2?
Oh yeah, possible.
Is that allowed to happen for these types
Oh
of
yeah,
questions?
of course. Depend on the situation.
Okay.
So there's no default that N1 cannot be more than N2, right? There's no
Okay. That does that only matter with the independent samples?
That's right.
Okay. Thank you.
Okay, so since S1 is bigger than S2, so P values will be 2 times F CDF, whatever that formula tell us, right? F naught 10 to the 99, degree freedom of N1, and then degree freedom of N2, right? So those are the formula we're gonna use here. Okay, so there we go. All right, we got that out of the way. All right, because again, that's only applied to two-tail.
For these problems, do we use the degree of freedom of the smaller one again, or
No, both sample, Matthew.
both?
Yeah. Yeah, only for the mean, then you decide which one is smaller. But this one here, we do both, yes. Okay, so p-values equal to 2 times the probability that f naught is bigger than 1.024. So we get 2 times with f, CDF, 1.074, and then 13, oh no, 10 to the 99, my bad. Okay, so that's what's the input for our p-values. All right, 2 times FCDF, 1.074, 10 to the 99, and 13s and 13s, and they both the same sample size, right? Right. So again, the only reason we're using that because it is two-tailed, so we have to do a comparison between S1 and S2. So if S1 is smaller than S2, then we're gonna go with the first formula. If S1 is bigger than S2, then we go with the second formula. In this case, S1 is bigger than S2, so we have to go with the second option here, right? For the two-tail only. Does that make sense? Okay, yeah, so that's the only reason we go for that. And then you just put into your calculators and see what happens, right? All right, so here's the calculator again. When you select FCDF, right? So I'll walk you guys through one more time. Second bars, and scroll down all the way until you see FCDF, and you press enter. It's gonna ask you for the lower bound, and of course we're gonna put in 1.024, right? And the upper bound, of course, will be 10 to the 99. And degree freedom of numerator is 13. And then degree freedom of the denominator also 13. And then you paste it, right? So if you have a TI-83, TI-84, you just input in this order, and it should also give you the same answer, all right? And there we go. And don't forget to times it by 2 because it's two-tailed. So we get 0.9665. Okay. All right, got 0.9665. There we go. So this gives us 0.9665. So comparison, same thing. If p-values is less than alpha, then we reject the null hypothesis. P-values is 0.9665, alpha is 0.05. So clearly you can see here that 0.9665 is not less than 0.05. So do not reject the null hypothesis. And in conclusion, we have to state it whether we have enough evidence to support the claim or we don't have enough evidence to support the claim. So the claim is the standard deviation of the red blood cell mass in the fly animal different from the control animal. We don't have enough evidence to support that, right? So that's the conclusions.
Do you mind scrolling up a little bit, Professor?
Uh-huh.
A little bit more, please. Something.
All right, are we okay with that so far? Yeah, so same procedure, right? Just like chapter 10. Okay. All right, so one last example here for section 11.4. So this one here, just like section we're asking, is that N1 always going to be less than N2? The answer is no, right? So here's one example where N1 is more than N2, right? So we have a researcher wants to know whether the state quarter have a standard deviation weight that is less than traditional quarters. He randomly selected 18 state quarter and 16 traditional quarters, weigh each of them, and then obtain the data below. Test the researcher claim at alpha equal to 0.05 level of significance, assuming that the population is normal. All right, so now what's different from example 3 in comparison to example 2 is that in example 2, they do give you the standard deviation right away. In example 3, the standard deviation is hidden. They just give you the data. Now, this is something that you will see on your homework, right? So they just give you the data and you have to use the calculator to find the standard deviation by yourself, okay? So go ahead and input the state quarter into L1, right? And then the traditional quarter into L2. And then from there, you can find your sample standard deviations, okay? So go ahead and try that out. And once you got that done, go ahead and set it up from step 1 to step 6 to see what is your conclusions, okay? Go ahead and give it a try, please. All right, so now you have a chance to experience it to make understand much better. All right, let me give you that list a bit bigger so you can put that to your calculators. All right, if you're done, put in the chat box your F naught and your decision in the end, okay? That's how we check the answer.
Professor, I have a question.
Yes, Victor.
Do we calculate the data together or do we calculate them individually?
Individually,
Okay.
you put them into two lists and you calculate the standard deviation for each list.
All right.
All right, all right. So after a few debates, we agree with that should be the answer. Yeah. Thank you, Jackson. Thank you, Victor. Thank you, Austin. Yeah, just once you got your S1 and S2, Alisa, you can just follow example 2. It's exactly the same, just different numbers. Yeah. Try that. If you have question, Alisa, which step that you are stuck on, I can help you with that step. But I do really want you guys to try it out. Okay? Try it out.
I just think I'm doing everything wrong. But I think, I don't know, I may have entered it wrong in my calculator or something.
For which one? For S1 and S2?
Yeah.
Yeah, so make sure you enter it right, because me and Adam and Jackson, we were debating. So I got a different answer from them, and I end up making a mistake very slightly. So we have that agreement.
I don't know if I entered it in wrong, but for S1, I got 0.0482. So I don't know, maybe I entered it wrong.
For S1?
Yeah.
Oh, you cannot use sigma. You have to use S, Lisa. This is not population. It's a sample.
Mm. Oh, yeah.
Does that make sense? Because what the number you gave me, that's for sigma.
Okay.
Sigma for population. This is the 2 sample. It's only 18 sample. So we have to use S, not sigma. Yeah.
Okay.
Does it make sense?
No, but I'll figure it out.
No, because the number you gave me is 0.0482. Yes.
Yes, that is correct.
Yeah. If you look at your calculators, do you see the sigma sigma x? We're not using sigma x. We have to use sx.
Okay.
And
That
that might be the wrong one. Yes.
Okay.
Uh-huh.
That would make
Yeah,
sense.
I just share with you. I share with you, not the same one, but I'm just gonna share with you right here. Okay. So for example, I have list one here. When I calculate the stats, right? I calculate that. Okay. So you can see here that you see S of X and then sigma of X.
Yeah.
We're not using sigma. We have to use an S, because S stands for the sample standard deviation.
Yes,
Make
it
sense,
does.
Alisa? There you go. So therefore, on your list, when you do that calculation, you don't use sigma x. You have to use sx, because we have 18 quarter as a sample and 16 quarter also a sample. You cannot use the other numbers. Okay.
Okay.
So that's explain why you get 0.482. Yeah. You have to use the number above that. Okay.
Okay.
So all your entry are correct. You just use the wrong number. Okay.
Yeah. Okay. That makes sense.
Yeah. So let me see. For your S2, Do you have 0.6456?
Yeah, I went ahead and changed it to 0.0689.
That's the one, yes, because you have to use the one above that, not that one. Okay. Right. Remember, sigma is for population. S is for sample. Okay, Alisa.
Okay.
Yeah.
For the next step for p-value, sorry, I don't know why this is, maybe math is not my thing right now. But for some reason, like some things aren't connecting for,
Okay, very important, Lisa. Which tail do you have?
that I struggle, that I don't know, that I don't know how to tell.
Well,
I
look
think
at
less
the.
than, right? So.
So which tail is that,
left
Lisa?
tail, or
Left tail. There you go. Okay. All right. So you write down sigma 1 equals sigma 2, sigma 1 less than sigma 2, right? And then what did you get? Did you get the same F naught? You're probably not gonna get the same F naught because you're using the wrong number for S1 and S2. So you might want to go back and fix that to get your F naught. Okay.
Okay.
And because the F naught is not correct, therefore your p-value will also not gonna be correct. One little number can change the whole game.
Yeah.
Yeah.
Wait. Okay. Yeah, because I ended up getting the answer that you put, the 0.5203.
And because we are using left tail, your p-value, you're gonna go with this one right here. Okay, Lisa, you're gonna go with this command for your left tail. You see that?
Yes, I see that.
So you're gonna go 0, F naught, and then degree freedom of N1, and then degree freedom of N2, and that's how you get your p-values. Okay. And that should take care of that problem.
Sorry, can you show how to get the degree freedom?
The state quarter have 18, so you take 1 away, you get 17. And the traditional quarter have 16, you take 1 away, you got 15. That's how you get degree of freedom.
Okay. And okay, that makes sense.
All right, so everyone should be on the same page now. Do they all got the same answer, or you got something completely different? Thank you, Julia. Thank you, Matthew. Alisa, you should be okay now, yeah?
Yeah, just I always mix up getting like where to find each like right now I'm looking for FCDF calculator because I get confused and then I find var stats on accident and then regular CDF and normal PDF. So I'm trying to find
you have to press second vars and then you go down all the way to the bottom. That's how you find your FCDF, okay?
FCD. Okay, thank you.
Right. It's right above binomial PDF, right? So FCDF is where you go find it. Yeah. Any CDF, you're gonna go second vars, and that's the way to go. Okay, so you can see here, little change will make the problem completely different, right? So here we have 2 sample, and if we use in the population, everything will fall apart after that, right? So be very careful with that, okay? Because the formula stated that S1 squared divided by S2 squared. So you're gonna look for that S on your calculators when you find that standard deviation, okay? Watch out for those little steps. All right, let me go ahead to attendance real quick. All right. Okay, so that should look good for today. So tomorrow we will finish the last 2 chapters, but technically only 1 section from each chapter. So 2 more sections and we are done with stats for the summer. Okay, and again the exam will be on next Monday. And I mentioned yesterday, review your first 2 exam again if you can, and you know, once you look at chapter 11 and 12 and 13 through the homework, you should be ready for the final. Okay, the final is next Monday.
I just wanted to kind of add something.
Yes,
I will be having tutoring sessions today from 6 onward. Well, let's say 6:30. And just to give me some time to grab something to munch. And then go from 6:30 to 7:30. Can go even to 8, you know, I mean to 7:30 if you guys need to. Now, since it's going to be the finals, you know, review any of the previous material or any of the, if you had any trouble today, like at the end, you know, stop by. I can help you out, go through the process, you know, or even think about some of the steps a little more deeply so you can kind of see the logic of it all. And yeah, so today at 6:30 I'll be posting, or before 6:30 I'll be posting the link to the Zoom session, and I'll see you there.
All right, thank you, Edward. All right. Okay, so you have questions for me, stick around, or if you want to you know, have one-on-ones with that example, stay around. If not, enjoy the rest of the day. I'll see you back tomorrow.
Thank you.
Thank you, Katie.
Hey, Professor, I'm
Hey,
just going to get the
Professor.
notes by watching the video that they post for what I
Oh,
missed
yeah.
yesterday. So, bye.
Oh, you should be okay with the notes, Matthew? Okay, sounds good.